Okay, good morning. We're reconvening for the second group of talks this morning. The next talk is going to be given by Leonardo Dantas from Federal University of Rio Grande do Norte, and he's going to be talking about mechanical control of adhesion and motion at the nanoscale. And since we're going to record, the guys there. Since we're going to record, then I kindly ask you that if you have any questions, then you wait for the microphone.
Hello, good morning. My name is Leonardo. I'm going to present this work here. And this work has two parts. The first one will be talking about controlling adhesion using strain. The second part will be talking about controlling motion using curvature. Okay, this first part. I'll give a bit of a background on what I'm working on. Basically, when you're talking about mechanical properties, you mostly think about tensile tests. So you pull a material, and then you get the Young modulus, you get the strength of the material, the ultimate strength of the material. You can get from this kind of curve, stress strain curve, if the material is brittle or ductile. But I'm not that concerned about the mechanical properties in this work in particular. I'm mostly concerned about properties that change when I apply the strain to the material. So I think the most classical case would be the piezoelectrics, where you apply a strain to the material and you get some voltage. And there are many properties that are like this. For example, this is a more recent example, where these researchers from Connecticut, they apply strain to a material, and then they change the color of the material and also the transparency of the material. This is a polymer, and they call this kind of material mechanochromic. But this kind of controlling properties with strain has really been aided by the discovery of 2D materials, because 2D materials typically, they withstand much larger strain values than 3D materials. For example, if you have graphite, it breaks with, or diamond that are carbon in 3D, they break with small strain values. If you have graphene, it breaks with much larger strain values. If you have silicon, when it goes to the 2D with silicene, you have another magnitude increase in the maximum strain. And these two last there, quartz and PZT, are piezoelectrics. And you can see that in the 2D realm, you have piezoelectrics that are those two here that withstand much larger strain values than, than the 3D materials. So it really opens a lot of possibilities of controlling properties applying strain. So, for example, before talking about the properties that you can control with strain, I'll talk a bit about how you can apply strain to materials. You can apply in 2D materials basic strain in three different manners. You can apply uniaxial strain, where you pull in one direction and allow the other one to relax, so it will usually contract in the other direction. You can apply strain in a biaxial manner, like this here, where you pull in both directions, so it will become strain in both directions. And for materials that are 2D that have buckling, like this one here, this is phosphorine, you can also try to apply tension or compression in this direction here. For graphene, you wouldn't be able to do this, but for materials like phosphorine or silicene, you could do this. And how much can you change the properties of a material by applying strain? So this is an example here for MEOS2. It usually is a direct band gap semiconductor. And if I apply, in this case here, tension using biaxial strain, you can see that you can really tune the band gap by a lot. So it can go from 1.7 here all the way to metallic here, if you apply enough strain. You have other materials, like, for example, here, phosphorine, that can also control the band gap. And this is for many different methods. This here is most likely the most reliable, this is GW calculation. So you can see here that by applying biaxial strain, you can go from 0.8, maybe electron volt of a band gap value, all the way to around near 3 electron volts. So you can really control a lot the band gap of phosphorine by applying biaxial strain. If you actually compress the material in the perpendicular direction, you can actually make it metallic as well. So you have a lot of flexibility on electronic properties in phosphorine by applying strain. So, but you can also control properties that are not electronic, that are properties that are dependent on the lattice of the material. This is an example here for thermoconductivity. This is a silicon and diamond nanowires and thin films. And you can see that since this is like not a 2D material, the maximum strain values that they apply is much smaller. But even then, you can really control by a factor of half. You can decrease a lot the thermoconductivity by applying strain. More recently, and this is more similar to what I'm going to show in this presentation, some researchers have shown that you can also use this kind of strain to increase the size of pores. So for example, here they have an MEOS2, and they create some pore in this material. They remove some atoms. And what they see is that if you pull with biaxial strain, so we pull in both directions, so the pore has to increase, right? So by doing this, they can control the water flow through this kind of pore. And they also see that for this kind of pore that they created here, you won't have salts passing by this kind of pore, so you can actually use it as a purifying filter. Another example that I think is clever, more clever than the previous one, is if you use a material that already has pores, like this one here, you don't have to create the pore. It already has the pores that you need. So in this is similar to the previous works. They have a material with some pores, and then you apply biaxial strain to the material. The pore size will increase. They show here that it increases by quite a lot. And by controlling the size of the pore, you can allow the flow of water through this pore. And the salt, once again, won't pass through the filter, and you get some pure water after the filter. Okay, so what I'm going to do here, what I'm trying to show to you, that can also control adhesion with strain in 3D materials. But I want to see what degree you can control this strain, this adhesion applying strain to a 3D material. And I also want to talk a bit about possible uses of this effect, since I think this is the first demonstration of this kind of controlling adhesion with strain. This work is published this year in Carbon, and there is also a feature on a website about this work, Science Trends. So this is more like general public than this one. This is the paper that shows what I'm going to talk about here today. And I'm going to talk about this material, Coffee 1, Covalent Organic Framework 1. This is a layered material, this Coffee 1. It was synthesized in 2005, so quite a long time ago. And this is a layered material. What I'm going to be studying here is the 2D form, just a single layer of this layered material. There's some works on the theory about this material as well. And it's composed of carbon, boron, hydrogen, and oxygen. And there's quite a bit of methods, so I'll be very brief in the methods part. If you want to talk a bit about something more specific about the methods, I can talk a bit about after the talk, show some more of the methods. But I'm going to do simulation with 3 methods, with ReaxFF, with DFTB, and DFT. For ReaxFF, I'm going to use lamps. This is the time step I'm using for the dynamics. I'm going to be using, in some cases, a thermostat. In those cases, I'm going to be using nozzle hoover. For DFT, I'm going to use this package. I'm going to be using PBE with van der Waals correction. And this is the time step that I'm using. And for DFTB, I'm going to be using this package, DFTB+. And the time step for the dynamics will also be 1 femtosecond. Okay, so how can I calculate adhesion between 2 materials? I'm going to be studying adhesion between graphene and the Coffee 1. So this is the definition, the formula here. You calculate the energy in a reference state, like this one here. And then you calculate the energy in this other state, that's in equilibrium with both materials very close to each other and interacting. And this is energy per area, so we have to divide by the contact area of the material. The basic idea is this is the kind of quantity gives the work that you need to separate these materials from contact to infinity in a vacuum. Okay, that's what I want to calculate. And before showing what I did, it would be nice to know why I'm doing this, right? Why do I think that in this kind of material, I should have some dependence of adhesion with strain? And I'm going to show why I think this should happen using this simulation here. This is a video. And this was obtained with DFT, this calculation here. What I'm basically doing is I have an optimized material with DFT, and then I apply some strain to the cell, allow to relax in the other direction, and then optimize again, and then stretch a bit more, optimize, stretch a bit more, optimize, and keep doing this with this unit cell here. And what I observe is this. You can see that as I increase the strain, it will compress in this direction and keeps compressing, compressing. And then there is a transition here. I'll show what's happening in this transition here. And you can see what's happening in this slide here. This is happens between 14% strain to 14.5% strain. What happens here is that I'm compressing the material, and when I increase the strain by this value, the material goes out of the plane. And why this happens is that I'm compressing a lot, so it's contracting a lot, this material. So in this region here, there will be some repulsion. And the way to reduce the repulsion in this region here will be to rotate the rings outside of the plane. So by doing this, you create space, and then you can have a further contraction in the perpendicular direction. And the basic idea is that since the material is no longer planar, before that, you have material that's very planar, so I put graphene on top. It would have very good contact area. When I have the material that's bending out of the plane, I expect that graphene would be a bit suspended above the substrate here, so it would decrease the effective contact area. Effectively, the number of atoms in contact would be smaller in this case here than in this case here. So I expect that the adhesion would decrease when I increase the strain in the material. Okay, so I have to do this calculation. There's some problems here. Ideally, would like to do this just with DFT? Yes. I'm not measuring how much energy, just applying the strain, relaxing the structure.
How do you know that things are not rearranging in a way that you're destroying the whole thing or creating some other kind of molecule?
It's quite organized, like you can see here. It's not really, all the bonds stay in place. Usually when you, in this kind of material, when you break it, it becomes much more disorganized. Like if an atom is free, it will be able to bend each other. And you can also see if you run dynamics, it won't be very disorganized. It will stay in place.
Maybe you should calculate total energy and see whether you have different kinds.
That's true, that's true. But I don't have this data here, but that would be something that's important. I agree. Okay. So I went to this calculation, but the problem is I need to have a graphene that's large enough to be able to stay here above this suspended region, so it cannot be too small. I also don't want graphene to interact with each other. I just want to have interaction between graphene and coffee-1. Additionally, I also want graphene to adjust to the configuration of coffee. So if I just put graphene on top of this material, coffee-1, and allow it to just a single point energy, I'm not being very fair because graphene is it can bend, it's a malleable material, so maybe it would deform to fit the surface of coffee-1. So I really have to allow graphene to evolve in time to see if it goes to if it's suspended or if it goes in and keeps in contact with the coffee-1 surface. So overall, the kind of structure that I'm thinking about doing the calculation is pretty large, this size here of atoms. So for DFT, that's not possible, at least for my kind of computational power that I have available. So I want to do this calculation with molecular dynamics, classical potential, in this case, ReactFF. Okay, so before I can do this calculation, I have to see if ReactFF actually reproduces the results from DFT. So I did some geometry optimization, and you can see that the unit cell is a bit different, like it's a bit smaller. But overall, the shape of the material is quite similar. If I calculate the bond length, it's quite similar. But if I go to dynamics, if I put some temperature and allow it to evolve in time, I can see that ReactFF does not really reproduce the geometry of the material at a temperature that's non-zero. What I see is that with the DFT, I have this kind of small rotation of the ring, but the equilibrium position of the ring is in the plane. So it will rotate a bit, but will always go back to the initial position. In ReactFF, this phenyl ring here, it rotates permanently. The equilibrium position is outside of the plane. So this is a problem for us. If we do the calculation of this kind of configuration, we have no guarantee that we will get a result that represents the real result. This was a dynamics that I carry out with React, and this with DFT. Just dynamics, like I get the material that I optimize from DFT, and then I put in, yes, this dynamics with DFT, dynamics with React. And I just put in I run ab initio molecular dynamics in this place here, and here this is classical molecular dynamics. And it really is different. Like if you run with DFT, it will oscillate a bit over time, but it will stay planar. But in classical dynamics, molecular dynamics, it will rotate outside the rings, outside of the plane, if in the rings, and will remain outside of the plane. I believe there is two minimum for the ReactFF. There is one that's in the plane and one outside of the plane. But for ReactFF, the minimum energy, the global minimum, is outside of the plane. So it will, there is a energy barrier here. It will stay planar if I'm optimizing. But if I give temperature, it will be able to get out of this local minimum and go to global minimum. That for React is this one here, outside of the plane. Okay, so how I want to measure adhesion? I'm going to talk a bit about this problem of React later, but the plane is this one here. I'm going to optimize coffee 1 using DFT. And next, this will be small. I want a bigger unit cell, so I'm going to replicate this unit cell to use with React. And then I'm going to fix the position of coffee 1 to prevent this kind of ring rotation. And then I'm going to add graphene to the surface of the coffee 1. And then I'm going to do some very extensive process of minimization, optimization, of minimization and thermalization of graphene on top of coffee 1. The idea of this part here is to allow graphene to really achieve the minimum range configuration in this on top of the coffee 1. I'm using here 1 Kelvin, but there's nothing special about this temperature. I try all the other temperatures, 10 Kelvin, 100 Kelvin. I'm basically using 1 Kelvin because what I want here is just find the global minimum of energy. And for this value here, I got a better result than for the higher temperatures. Okay, so the main problem that I have here is I know that coffee 1, if I put in a dynamics this material with ReactFF, I don't get the right geometry. But I want to use the fixed geometry of coffee 1 with React to interact with graphene. So how do I know that if I fix the geometry, coffee 1 React gives me the right values of energy? That's the problem that I have. So my idea here was to actually map the potential energy of ReactFF. And since I'm going to be working with graphene, to map the potential energy, I use a benzene molecule. So I fix the coffee 1 surface, and I actually swipe I move around the surface, the benzene. And for each point here that I have for this benzene, I calculate an energy value, comparing with a reference value that's far from the surface. So for every point here, I calculate an energy value. And this keeps going. And it keeps moving up, but very slowly because there are lots of calculations to be done, over 15,000 single point energy calculations. So it's not 0.2 angstrom between one calculation and the next. So what do I get here? This is what I get with ReactFF. So for every point, I get an energy value, and I plot in the surface here. And since I'm going to be doing lots of calculations, it would be difficult for me to do all this with DFT. So I actually use DFTB. But this DFTB here, it actually reproduces DFT very well. Like the unit cell is very similar. If I run dynamics with DFT and DFTB, it's basically the same. And it is also planar with DFTB. So I'm comparing these results that are actually quantum true, but not as good as the previous with DFT, with ReactFF. And I see that there are some difference, but for the most part, if I fix the geometry of coffee one, the energy values that I get are okay. Because mostly the interaction will be van der Waals interactions between, and some Coulomb interactions between the coffee atoms and the benzene. And I also did a map like this for the structure that's bent, that's out of the plane, twisted. And I also get that, for the most part, the energy values are pretty similar for DFTB and presumably DFT and reacts. So I cannot trust reacts on dynamics, but if I fix the position of the coffee one atoms, the energy values that I get appear to be reliable. Okay, so remember again what I'm doing here. I'm putting graphene far from the surface of the coffee one, and then I bring it close together, calculate both energies, divide by the area, and for every value of strain, I do this calculation again. And the result, yes?
Can you go back? So in red is the
higher energy, and blue is
higher
lower
energies means that it's more probable that it will bind there, is it?
No, it's I'm not binding. I'm keeping the distance fixed, so it's just scanning the surface and just getting the van der Waals energy values.
So that's the position where the interaction is greater.
This here is the lowest energy. It's the region where you have the pores here. So no atoms, very little interaction. Okay, so I'm going to be doing this, and this is the value that I get if I do this kind of calculation. Fix coffee one, put graphene on top, measure adhesion. For every value of strain, I repeat this calculation, and I get this kind of value here. And as I expected, when I apply a large strain value, I have this rotation here. It goes out of the plane, and I see a large decrease in adhesion value, a decrease of about 25%. So I really can control. I don't have much tunability. I have like a 1 and 0 state. Basically, I have a high adhesion state when it's planar, and as I apply strain, it will eventually rotate the rings. And when they rotate, I have a low adhesion state. So I want to see what kind of thing I could possibly do with this kind of controlled adhesion. And I'm going to do the simulation here, and just some important detail of this calculation here. Since in this calculation, I'm going to be doing a dynamics, and I'm also allowing the coffee one atoms to move. You can see here that we have a ring rotation in here. And the detail that's important, is that when you have this kind of just a minute. The important detail is that when you're doing the calculation, all calculation using ReactFF, the effect is different. You have high adhesion when the strain is high, and low adhesion when strain is low. So for reacts, the effect is inverted. But I just want to show what kind of thing you can do. This kind of effect that I'm showing here, as long as you can control adhesion of strain, you can do this kind of effect here. If the strain is high if the adhesion is high with high strain or low strain, it won't matter for this kind of application. So okay, what I'm doing here, I put some graphene on top of this material here, and I want to transfer this graphene between the two coffee substrates. So initially, this guy is with high strain, so adhesion is high here for reacts, and this is low adhesion. So as I move them in contact, I can see that adhesion is high here, so it will remain bonded to the coffee one on top. So what I'm going to do next is I'm going to reverse this strain. I'm going to decrease the strain here, and I'm going to increase the strain here. So now adhesion is high at the bottom and low at the coffee one on top. So as I move down, now adhesion is high on the bottom, and I can transfer the graphene. So we say this is kind of a tweezer in a certain sense, because I can apply strain to the material to pick it up and then to drop it off. Well, this is the idea, at least. I'm going to talk a bit about later if this kind of stuff can be realized, because the strain value that I need is quite high. And right now, this is not possible to do experimentally. Get the strain values into the materials that are this high. There's another possible application. I didn't run calculations here, but it's just illustrating another possible use of this kind of effect. Some time ago, some researchers showed that if you control the surface energy of graphene, and for this paper here, they use an electric field. So they use electric field to control the interaction between this substrate and the scroll here on top. So basically, if you use the electric field to increase the interaction between the substrate and the scroll, it will start rolling out. So it will roll out. If I do the opposite, if I use the electric field to decrease the interaction between the substrate and the scroll, it will roll in. So the idea is to do this kind of effect of controlling the interaction between two materials, but instead of using electric field, using strain to do this kind of effect. So again, how can this be done experimentally? And to see if this can be done, first, you can actually apply strain to 2D materials. And there are four ways of actually of doing this. This is one way. You put a 2D material on top of a elastic substrate, and you bend it. When you bend it, the part here on top will become tension. Another way is you have a very elastic substrate, and you put the 2D material on top, and you stretch the elastic substrate. Within a certain degree, it will also stretch the 2D material. You can also use piezoelectrics, and you can also use thermal expansion. If you have material that expands a lot with temperature, and you heat it up, it will expand more than the 2D material, and you can actually apply strain to the 2D material with this kind of method. The two methods that are piezoelectric and thermal, they are biaxial, so for this kind of effect, it wouldn't be helpful. But the first two, they're uniaxial strain that you get, and the maximum strain that you get so far in the literature is 4%. So it's still too small to be able to get this kind of effect that I'm talking about, since I need about 14% strain to be able to move to have the coffee moving its rings out of the plane. Okay, this is the second part of the talk. This is a different work from the previous one, but this is a kind of a similar idea of controlling, in this case here, motion using mechanical cues. So okay, can you actually, nowadays there is very good control of atomic motion in the nanoscale, if you can afford and if you have the time. So for example here, not showing this video, but some time ago some researchers did a video where they actually move atom per atom, and they have this interaction of this boy here playing with this ball in a movie. So they did 242 still images moving these CO2 molecules on this copper surface. And the idea was to show that they can control precisely where each atom of each molecule of CO2 is on the surface. But it takes a lot of time to do this. They say in this feature here that they took 2 weeks and long days for people to be able to do this kind of movie, to do these 242 still images. So this is not feasible. This kind of control using microscope to move objects, it's difficult to do this. For one thing, it takes time. And for another thing, the problem is that it's a macroscopic apparatus that's moving a nanoscale object. So efficiency cannot be good in this kind of movement of objects. Most of the energy will be used to move to actually displace the macroscale object, and the actual work that we're doing on the sample is very small. So how does nature does this? How, for example, this is an example that I found in this paper. Let's say you have a vascular accident, and then you have a vascular accident in some place, in some person, and then how does do the cell knows that they have to get in a certain location of the body? What people found out is that cells tend to move from soft tissues to hard tissues. When a person has a vascular accident, it will start making fibrotic scar tissues, and they are very stiff, this kind of tissue. So naturally, since they are very stiff, the cells will go to the region that's stiff, and lots of cells will go to the region where there was a vascular accident. Okay, and overall, this kind of controlling biomotion using mechanical cues, the overall name of this is mechanotaxis. And they really have a good control of this. For example, here, they get two polymer substrates. This one is stiff, this one is soft. And they put lots of cells on the surface. And they see that if you allow the cells to move on the surface, they will naturally go to the region of the substrate that is stiff. So naturally, cells go to stiff regions of either in the body or in substrates that are from polymers or other materials. And some time ago, they actually found that this kind of effect also happens in the nanoscale. This was published some time ago, 2015, and what this was found was that if you have a substrate that has a gradient of stiffness here on the bottom, and you have a mover on top, it will naturally go to the region of the substrate that's more stiff. They control the stiffness by coupling the substrate with various coils. So the coils here are more stiff, and the ones here are more soft. And so it will naturally move towards this region that is stiff on the substrate. And there, basically what they found was that when you have a more stiff coil, the fluctuations of the substrate is smaller than in this case here where it's soft. And the interaction energy will be a bit higher in this region here on the right, where the substrate is stiff. So the idea of this work is to have some different way to move objects that does not rely on gradient of stiffness, but another gradient. And this is our proposal, this kind of structure here. How did we do the calculations? So for this one here, use the charm potential. Within lamps, we use no thermostat, only NVE. Our time step was 1 femtosecond. And for the oscillators, we have both CNT and graphene nanoribbon oscillators. For the CNT, the mover will be 9.0 with this length, and the substrate will be this length, and it will be armchair. For the GNR, we are going to actually try two different configurations, zigzag and armchair, and the substrate will always be armchair. And this is the initial configuration. The beginning of the simulation is easy to predict what's going to happen, because this nanotube here, it is outside the substrate, so if it moves inside, it will really decrease the van der Waals energy by moving inside. So this is the first step of the simulation. It will move inside to decrease the van der Waals energy. No, just van der Waals will pull it inside. But as it moves inside, it starts slowing down because the elastic energy is increasing. It will stop eventually, and then it will go back outside. Like here, go back outside. So what's happening here if we are talking about energy? So like I mentioned right at the beginning, what's driving the oscillator is van der Waals energy. It will go inside, it will really decrease the van der Waals energy of the nanotube. And then it will keep, this van der Waals energy will become, at least in part, kinetic energy. So it will start moving inside. As it moves inside, the elastic energy will increase over time. Eventually, it will convert all kinetic to potential energy, and then it will go back. So once it will convert the elastic potential energy into kinetic energy, and it will move outside of the oscillator, and eventually it will exit a bit, increasing the van der Waals, but will quickly go back inside the outer substrate. We did a different setup as well that does not involve van der Waals energy gradient. Here we have a double oscillator, so in this case here, in every instance, the van der Waals energy is constant. So we basically have just conversion of kinetic to elastic and back again in this kind of oscillator here. So why is this happening? Why do we have this kind of motion? And you can understand this by considering the elastic energy. If this is considering that the nanotube is a thin rod. If you consider this, the energy per unit length will have this form here. This is the elastic modulus. This is the moment, area moment of inertia. This is the curvature of the nanotube. In this case here, of the thin rod. So basically, I'm considering that this is fixed, and I want to see if I have a force, if I have a gradient of curvature. And indeed, if you have a gradient here, I can have a elastic force that will tend to first slow down my mover, and then eventually make it stop. And in this kind of structure, Archimedean spiral, as you move inside the structure, the curvature will increase continuously. So we have this kind of increase of curvature as you move inside the spiral. So what we have basically in this kind of effect is a gradient of curvature that creates a force that tends to first slow down the mover and then move it back outside of the substrate. We can also do this kind of effect with graphene nanoribbons. So if you put a nanoribbon, this is nothing special about the nanotubes. You can, as long as you have a gradient of curvature, you can have a material that's moving inside and eventually will stop and then move outside. This is I mentioned before, like previously here, in all cases I'm using a mover that's zigzag and a substrate that's armature. What I'm trying to do here in this next one is compare what would happen if I have this case here. In this case here, both the mover and the substrate, they are armature, and on this one here, the mover is zigzag and the substrate is armature. And as you can see here, if you, for this case where both are armature, you have some friction, and it stops moving very quickly. Whereas in the case where you have this kind of substrate that's armature and a mover that's zigzag, you don't have much friction, it keeps moving on and on. So why is this happening? And first, just show the energy. As I mentioned before, you have some conversion of van der Waals to kinetic energy, and then eventually to elastic and back again. This is for the case where there are different, this is armature and this is zigzag. For the case that both are armature, you basically, after some very short time, you basically just have noise. So to explain what's happening here, you have to consider the effect that they call super lubricity. So I have here two graphene sheets that have different orientations. And on this figure C here, I'm getting two graphene with this orientation, and I'm stacking one on top of each other. So naturally, it will go to this kind of configuration that has a AB stacking. If I stack one of this configuration and another this configuration, I get this kind of pattern here that you don't have very clear stacking pattern on this one on the right. And what I'm showing here is basically an energy map. It's similar to what I showed before for the case of the controlled adhesion. I'm moving a small piece of graphene on top of this large graphene substrate. And on this case, on the top, I have a graphene that's armature with some orientation, and on the bottom, the same orientation. And naturally, they will have regions with low energy that corresponds to AB stacking, and then regions with high energy that corresponds to AA stacking. So for this case here, as you move the graphene on the substrate, you have energy gradients. So as long as you start moving the graphene on the substrate, in the case of the dynamics, you have energy gradients that will cause forces of friction to appear. And for this case here, you want to have a sustained motion of the mover. For the case that's on the bottom here, it's a bit different because when you displace the graphene that's on top, some atoms will gain energy, some will lose energy, but there's no real net gain of energy in this kind of displacement. So for the most part, if you look at the scale of energy here and here, it's much smaller here. And if I actually make it bigger, this kind of energy here won't increase. And for this case here, the bigger the graphene is, the bigger will be the interaction, this kind of energy gradient that I found here. So in this case here, I can basically, all surface of the graphene that's on the bottom is a net potential for the graphene that's on top. So it can move without requiring any force. So basically, in this case here, you won't get much of a friction force. On the case on the top, there will be lots of friction force. Again, how feasible is this kind of effect? So for one thing, they are able to do this kind of nanotube inside nanotube that's moving. So you can see here that it's inside here, it's moving outside, moving back inside, outside. So this kind of nanotube moving, it's being realized experimentally. And they can also make structures that have curvature in the experiments. But the main problem here for us is that the curvature that we have in the experiment is this silicon nanowire, and this is graphene kirigami. The main problem is that the scale is much larger than what we have in the simulation. So if the scale is larger, the curvature will be much smaller than what we have in the simulation. So it might not be possible for this kind of gradient of energy to move the oscillator. But it may be possible or not, but it's not straightforward. It's possible to make structures that are curved, but the curvature may not be enough to actually move the oscillator. So in the overall message of this talk, for the first part of the controlled adhesion, as I mentioned before, in the case of 2D materials, the maximum strain that you can get is usually quite high. So you really can control properties by a large factor when you're considering 2D materials. And we showed that another property that can be controlled by applying strain is adhesion. We showed this in this paper. And we also gave some idea of what kind of effect, what kind of application you can find for this kind of effect. On the second talk, the main message is that it's difficult to move an object in a nanoscale. It's not easy. Just finding is difficult, and moving is quite difficult. And you can actually have the object move by themselves by employing mechanical cues. And we propose a different kind of source of movement compared to literature. We are actually proposing that if you use gradients of curvature, you can actually have a mover drive itself on a substrate. So thank you for the institutions that host my research, and also for the institutions that sponsor the research, and also you all for paying attention. Thank you.
We have time for questions.
So you showed that Reax doesn't capture the right structure for your COF1
Yes.
structure, and
Yes.
whereas DFT does.
Yes.
But you did a very short ab initio MD simulation, 1.5 picosecond, right?
Yes.
Do you think if you run it longer, it could go to the Reax configuration?
I don't think so.